So this is technological innovation and new media. Once again, we are dealing with a topic of networks. So this is maximum as well as minimum share queuing. Uh, Pretty much easy topic for you, my dear students and young researchers. And you can reach me at dr.christoananth@gmail.com. Before beginning the session, once again, let me thank God for giving me this golden opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students, and young researchers. So, in today's class, we'll have a short introduction towards maximum minimum fair share. Then we discuss about FCFS, first come, first served scheduling policy. Then for the resource sharing, we will be having the maximum minimum fair policy. Then we will have the link capacity pre-allocation for the maximum minimum. Then we discuss about bottleneck links. Okay, so just like the entry point where we accept information and we transfer information, that we would be discussing. Then we try to analyze and then simulate this fair queuing algorithm. Then we discuss about empty as well as full queues. We discuss about the performance of the fair queue as opposed to the first in first out queuing procedure. Then we discuss about WFQ, weighted fair queuing. How you try to control burstiness is how we complete this class. So I have independent work for you. I will definitely post them in the Google Classroom. Please submit them, and at regular intervals I will be giving you some short videos to discuss the knowledge in our topics. So whenever we are dealing with resources, normally the problem is that if we have too much of resources, we can share it equally among everybody. But if we take in the case the resources are very much less, okay, so which means that we cannot share it equally among all the resources, okay, so which means that everybody will be having very less resources and you cannot equally distribute them one among the other. So how in this case we distribute the resources if we have scarcity of resources? So in this case we would be using this maximum minimum fair share where you will be having or you would be requiring a very small amount. So the requirement policy or maybe what we try to require from them, that would actually be satisfied. So which means that it will be equally shared, and definitely based on the requirement, based on the available usage, what we are actually using them, we can actually share among them. So for this we will be using maximum minimum fair share allocation process as well. So based on the demand it will be resource allocated. Okay, for example, I am requiring too much of resources, which means for me it will be allocated more. For example, you need not have to require these resources, means for you very less it will be allocated. So that is the maximum minimum fair share allocation. So no source gets a resource share larger than its demand. So what I require I will be getting, what you don't require you will not be getting. For example, you require only minimum, you will be allocated only that amount. Okay, and sources with unsatisfied demands get an equal share of the resource. So this is how you do. If I ask I will get, if I don't ask I will not get. So this is the first come first serve scheduling policy. So this maximum minimum fairness you will be achieving, and definitely you can increase the allocation for any participant based on the decrease in the allocation of some other participant. So maybe somebody will not ask for it, but somebody will ask for it. So somebody, those who do not ask for it, from them the resources will be taken and it will be given to somebody who asked for it. Okay. So this is the case of the statistical multiplexing. So you'll try to follow the FCFS, first come first serve scheduling policy. So the advantage is that you can go for traffic shaping, which means that for the ill-behaved flow where it involves larger flow of data packets or maybe burst of many data packets, that will punish itself, but definitely it will not be affecting, it will not create an impact on the other networks. So network congestion has to be avoided with the case of FCFS. Okay. So maybe in the even in the case of networks also this is the procedure. So this is an example of the maximum minimum fair packet scheduling. We will be using fair queuing procedure. So it will be giving the scheduling priority to the users who have achieved the lowest data rate. Okay. So in this case, we will be using round robin scheduling process. Okay. So that you can use it for the maximum minimum share. Okay. So by using this round robin schedule, you can go for higher average throughput, but definitely there will be low stability in the service quality. So if the instability, if it is throughout continuing further on and on, then definitely there will be users who will not be satisfied about a stable communication service. So maximum minimum fair resource sharing, you will be having higher average throughput. Definitely there will be spectral efficiency will be very high, and everybody will be using the better utilization of resources. As I told you, like what I ask for, I will be getting. If those who do not get from them, it will be taken and it will be given to me. So in the equal sharing, some data flows may not be able to utilize the fair share process, and the policy for the equal sharing also will prevent the network congestion procedures that is actually taking. Okay. So on the other hand, this maximum minimum fairness will be providing lower average throughput than the maximum throughput resource management. So no capacity might remain for the most expensive flows. So these are the situation for the happy consumers. Okay. So what are the cases for lesser happy consumers and what are the cases for more happy consumers? So maybe an expensive user, maybe like a mobile station, if it is situated at a far distance location, and maybe if there are higher signal attenuation problems as well. So this maximum throughput policy, it will have lesser expensive flows, which means that the consumers or the customers will not be happy. So for this case, if the customers are not happy, if the consumers are not happy, so compromise should be made with the maximum minimum fairness or maybe the maximum throughput that we are going to achieve. Okay. So if the expensive data flows achieve low service quality, okay, if that is there, so maybe to manage the overall network quality, if it is little bit degraded, okay, then you can solve this particular problem. So they will not suffer from starvation or they will not suffer from adequate resources. They will all be getting the adequate resources. Okay. So maximum minimum fairness for this policy will be having stable service quality and definitely customers or maybe consumers will be happy. For the maximum minimum fair link capacity pre-allocation, so it assumes that the resources are allocated to the flows in advance in opposition to the best effort networks. So best effort networks normally, like all the times, it will not be useful. Okay, so like maximum minimum fairness, definitely for the allocation of resources it will be very good. So let us take in the case we are considering high data flows, like we will be considering users or resources. For every data flow we will be having an initial node, a destination node or maybe final node, and then the data rate we will be considering. So the flow on the path through the network may be achieved by the parallelism or maybe parallel links that we achieve in a load balancing scheme. So we will be having an allocation vector x for which the ith coordinate is the allocation for flow. Okay. So this allocation vector we will be having the ith coordinate. It is nothing but the rate at which the user I is allowed to emit the data. Okay. So here the allocation of the rate x is nothing but the maximum minimum share, and for this you have the condition if and only if the increase of any rate within the domain of the feasible allocation must be at the cost of the decrease of already smaller rate. So we'll be having this maximum minimum fair allocation which may or maybe may not exist. So this is considered as a unique condition. Okay. So we give the higher relative priority for the smaller flows, and larger flows we will be categorizing the maximum minimum. So when the flow asks to consume more than the link capacity to the number of flows, so which means it is at any risk of having the bandwidth throttle. Okay. So this is the bottleneck link. As you can see through the bottle, through the neck of the thing, you will be having the data flow I, which is a link that is fully utilized, and all of the flows which is sharing this link will be having the data flow I, which will be achieving the maximum data rate. Okay. So here the definition does not forbid any single bottleneck link as well. That is to be shared across different multiple flows. Okay. So through the bottleneck link, we will be having like at least one link will be having all the resources being allocated, and it will be following the FCFS, first come first serve. Just like the bottle entrance, you will be having all the data information to be followed. So you'll have also an alternate algorithm as well for this maximum minimum fairness achievement. So for this we will be using progressive filling algorithm. So if you are allocating the resources well in advance, maybe you will have this progressive filling. You start with this one, all the rates equal to 0, and you increase the rates. You try to grow the rates together at the same rate or maybe at the same pace until one or maybe several link capacity limits are being hit. So the rate for the sources that uses the link are not increased anymore, because there is only one limit. There is only up to certain limit that you can hit, and after that there will be burstness. Okay, so you can continue increasing the rate for other sources as well until you meet the threshold. So all the sources that are stopped have a bottleneck link. So after that bottleneck link only you can hit the target. Right. So this is because they use a saturated link, and all other sources using the saturated link are stopped at the same time, because you are moving at the same rate, you are increasing at the same rate. Only up to the bottleneck link only it is going to send the resources, and after that it will be stopping. Right. So we have a smaller or maybe equal rate. Okay. So the algorithm continues until it is not possible to increase after the bottleneck link. So when the algorithm terminates, all the sources have been stopped at some particular point of time, and everything will be having that threshold limit, and this allocation you will be having an equal share, nothing but the maximum minimum. So we'll consider different strategies. We'll consider per flow queuing, queue management versus queue scheduling, work consuming, as well as maximum minimum fairness. Okay. So in the per flow queuing, the routers maintain the state for each flow. So every flow has been separated or will be segregated, and just like FIFO, first in first out, the queues are indifferent to the various flows. And here we will be using random early detection, where the amount of packets drop is directly proportional to the bandwidth of the flows. Then we will consider the queue management as opposed to queue scheduling. Queue management, we will be considering the algorithms that decide which packet can be dropped. Okay. But in queue scheduling, we will have the packets to get transmitted. As and when they get transmitted, you can decide them, you can schedule the policies, and you can make sure assurance the packet delivery. And then work consuming, you can do the work if there is work to be done, otherwise you need not have to. So if there are packets in the queue, then you can directly service them. If there are no packets, no need to service them. And then maximum minimum fairness, so it is nothing but an alternative index to the what we have discussed. So all users have the equal rights to the resource. So as I told you, for example, if I have access, or maybe if I have requirement, I can ask for it and resource will be given to me. So fairness is achieved if the user can increase the utilization of resource without decreasing the utilization of someone with lesser or maybe equal allocation. So if I am trying to utilize, then I will be given more resources. If somebody is not using, from them it will be automatically taken. So this is the analysis and simulation of the fair queuing algorithm. So first flow we will be having a bandwidth like 1, 2, 3 and so on. First flow needs a bandwidth of 3. Maybe the second one needs a bandwidth of 1. Okay. So the bottleneck bandwidth is considered to be 3. So that is the average limit. So maybe we can allocate, since 3 is the maximum limit. So you can divide by 2. 3 divided by 2, it is 1.5. So 1.5 you are going to allocate for each user. The second can use only 1. Therefore, we can give only 1 if it requires. Maybe if he asks for another 0.5, we can allocate for the 0.5. If he doesn't require, no need to allocate 0.5. So the basic idea is that you have to share the equal bandwidth. Like 3 is there, 3 divided by 2, 1.5 we are allocating as fairly as possible. Then we'll use fair queuing. So in the fair queuing, you'll be having maximum minimum index. So most fair algorithm is nothing but the round robin, like a bit by bit round robin algorithm. So there is one bit for each flow that is being serviced for every round. But definitely it is not practical. Okay, so normally you will have the, instead of bit by bit, you will use packet by packet round robin solution. So flow with the small size packets will be receiving lesser bandwidth than the flow with the large packet size. Okay, so in the bit by bit round robin algorithm, if we use in this scenario, it will not be practical. So if we go for packet by packet, definitely it will be helpful. So this is how the flows are considered with respect to each of the packet. So if there is no packet that is being transmitted, then there is no flows, and for each packet there will be round robin fashion. So there are some parameters. So this is the NA, which is nothing about the number of active flows. U is nothing but the available bandwidth, and R of T is nothing but the number of rounds that we have with the bit by bit round robin. And then we'll have the receiver R of T, where we'll be having the clock instead of the time. It is nothing but the time of arrival of the packet. Okay, and then for each arriving packet we will be calculating the finish time, which is nothing but R of TF. Okay, then we forward the packet with the smallest finish time, so it is nothing but dr of t divided by dt, which is equal to u. Okay, u is nothing but the bandwidth divided by the number of active flows n of u. Then we decide two factors. One is empty queue as well as full queue. So this is R of t versus t. We will have a flow for the slope equal to u, and this is two flows for slope equal to u by 2. So when the number of flows increases, the slope of R of t will decrease. So that is the thing. Okay, when it increases, the slope will decrease. So here for the bit by bit, we will be having two conditions. One is empty queue and then full queue. Let us take in the case the packet P arrives to the empty queue. So for this case, R of T0 is the arrival time and R of TF is nothing but the departure time. And P is nothing but the packet size. So for this case, R of TF is equal to the arrival time R of T0 plus the packet size P. So these are the two conditions for the case of NA, number of active flows, okay, for the U bits, okay, per second. This is for packet P and this is for packet P1 30 and packet P2 22. So this is the analysis for two cases, one for P1 30 and P2 22. Okay, so P1 arrives at T0. Let us take in the case. So R of T0 equal to 12. Okay, right. So P1 is equal to 10 bits. So for this case, 10 plus 12 it is 22. Okay. So P2 arrives earlier at another queue. Let us take in the case. So R of T0 is equal to 0. Okay. P2 is equal to 30 bits. Okay. For this 0 plus 30 it is 30. So since the finish time is smaller, so in this case, so smaller case we have to service first. So, but you, because it is bit by bit, it is not practical, it is not clear. So first packet would have finished earlier than the other packet. So the ordering of the finishing time in the fair queue is the same as that of the bit by bit. Here in the case of full queue, so if P arrives to the full queue, then the previous packet must finish before starting to the servicing of P. So in this case, Fi is equal to finish time of the packet I, Si is the start time and P is the packet size. So in this case, start time is equal to maximum Fi minus 1 R of T and finish time Fi is equal to start time plus the packet size P. Similarly, we can also analyze for this one R of T0 is equal to 4. So, two packets for C1 of size 2 arrive at T0 and 4 packets for C2 of size 1 arrive at T0. So, according to this, we can service packet in the increasing order. Based on the smaller rate, we can increase. For this one, like 8 and 6, we service first and after that 8, 7, 6, 5. So this is also another goal for the fair sharing algorithm. Like we can assure like more prominence for the users with less than their fair share. Okay. So we can calculate the bit B is equal to Pi plus maximum of finishing time Fi minus 1 Si minus D. So for the users who are trying to use the bandwidth too much, then for this case the finishing time Fi minus 1 will be more. For the less users, for the idle users, the Si minus D will be having more preference to the users who have been idle. Okay, so those who have been silent or maybe idle, they are giving more preference up to the D timestamps. So this is the performance of the fair queuing as opposed to FIFO queuing. So for the new flow, it is using lesser than the fair share. So this is the average delay per new flow. This is FCFS and this is the fair queuing. So this is the intersection point for which it is achieved for the throughput of one additional connection. So this is a generalized process approach for the worst case performance guarantee with the case of bandwidth and then delay. The weighted fair queuing plus leaky bucket, it corresponds to the worst case guarantees for the bandwidth as well as delay. We'll be having the leaky bucket admission control. So traffic is actually shaped with the case and of course control as well, and it actually regulates the traffic which is entering this entire network. So this is the weighted fair queuing. So this is the incoming traffic and this is the rate at which we are flowing this entire traffic. So this the rate is actually Ci. Okay. And this is this bucket. The size of the bucket is actually S, and these are nothing but the tokens which are trying to flow. So if you can observe, the tokens enter at the rate P, and this is the incoming traffic. This is the rate at which it is flowing to the entire network. So with the weighted fair queuing, you can control the exact traffic flows and you can assure that the bandwidth is being utilized properly. So this is how you try to control the burstness. Here the tokens are generated into the bucket at a rate P and the size of the bucket is actually S. The incoming packet should not exceed before using the token. So which means that when the bucket is full means no more tokens are actually produced. So this is how the maximum amount of traffic is injected to the network at one time and it is being restricted to the S. So since we are keeping this many condition, burstiness or maybe too much of data flow is actually controlled. And here the output of the packet is restricted between two lines and we are making sure that the slope of the admission rate is lesser than the peak rate which is C. So since we are making sure it is lesser than the peak rate C, we are actually controlling the burstness. So this is the bits injected versus the time, and for the two cases bucket empty and then bucket flow, we are having the limit to be S and after or maybe beyond yes, you cannot admit or maybe accept the data flows. Within that you can make the tolerable limit. So this is how you control the burstiness. So these are the independent works: image transforms, discrete, DFT as well as FFT, DCT you can go through and you can submit them, and of course the VoIP and the common multimedia applications you can submit them in the Google Classroom.